Hi, welcome back. This is section 4.4, problem number 2, part 1. This is going to be a two-part video because it's a long problem. The first question, it's giving us a function y equals 3x plus sine of 6x and a boundary. So in other words, we have an interval where we are essentially zooming in and figuring out what's happening on that interval. The reason why is because when you see a sine, you know that this function is going to be very repetitive, so there will most likely be infinite inflection points, infinite maximums, minimums, etc. So that's why we put a boundary on a problem like this. And there will be boundaries on other problems, but specifically for this one, if there weren't boundaries, it would take an infinite amount of time to solve. So the first step to finding inflection points are when concavity equals zero between a concave up and a concave down portion of a graph. Now we know that the second derivative tells us concavity at any given point on a graph. So if we take the second derivative, so we'll start with the first derivative, and the first derivative is 3 plus 6 cosine 6x. The second derivative is equal to negative 36 sine of 6x. And we know that if we set the second derivative equal to 0 and we solve, we'll find our inflection points because that's where concavity is 0. So we can divide the negative 36 across and we just end up with sine of 6x equals 0. Well, now we're going to take the arc sine of both sides. So 6x equals the arc sine of 0. And this is the hard part of the problem right here is there are infinitely many points of which sine will be 0 on a graph like this. So it's important, maybe not with this specific function, but we have to look at all of our options. So if I were to look at a graph of sine, it would look something like this. And remember, with arc sine, we're saying our output is 0. What is our input, x? And so we look, where's our output 0? Well, there's one there, there's one there, there's one there, and it's very periodic. And what you'll notice is with the sine graph, one of those occurs at x equals 0, one of them at x equals pi, one of them at x equals 2 pi, one of them at x equals minus pi, one at minus 2 pi, minus 3 pi, and positive 3 pi. And you can come up with sort of an equation for this, because you'll notice that for arc sine, it's always an integer times pi, whether it's a negative integer or a positive integer. And so arc sine of 0, we can write this is equal to a set of numbers, one that starts, so let's start the pattern. One's at 0, right? One's at pi, one's at 2 pi, one's at minus pi, one's at minus 2 pi. And if we follow the pattern, we'll notice that there's one at n pi, and there's one at minus n pi. So here's our set of numbers. And so you could see we could choose 3, and we'd end up with negative 3 pi, and 3 pi all the way up to infinity because it's a periodic function. So the next step is we're going to divide by 6, because we're solving for x, right? So we're going to divide everything by 6. And when we write our new set of numbers, we'll find that x is equal to a set of numbers of minus n pi over 6, minus 2 pi over 6, minus pi 6, 0, pi 6. So I've just divided everything by 6. Every one of these numbers I'm dividing by 6. And this is going to represent our set of solutions for the second derivative equaling 0. And so the key here now is we know there's infinitely many. They go in either direction, to infinity and negative infinity. But we want ones that fit between the boundaries of minus 2 pi ninths and 2 pi ninths, because that's where x has to hang out, and we're solving for x. So now that we know that, what we'll do is we'll write out for example, if you take your calculator and you type in 2 times pi and divide by 9, you'll find that negative 2 pi ninths 2 2 pi ninths as an interval is approximately equal to negative 0.698 to positive 0.698. And then what we'll figure out here is, well, where's our cutoff here? Let's start with negative and positive 2 pi 6. So 2 pi 6 is approximately equal to negative 1.047, and that's outside of our range on the negative side. And likewise, positive 2 pi 6 is equal to positive 1.047, and that's beyond our range on the right side. So these points, 2 pi 6, they're outside of our interval. So we can cancel 2 pi 6 and everything to the left and right, respectively. So now we're left with 3 possible x values that fit within our interval. Alright, so although we haven't proved that yet, let's prove that real quick. If I take negative pi 6, that's negative 0.524, and likewise pi 6 is approximately 0.524. Now negative 0.524 lies within our interval. It lies within our negative 0.698 to 0.698 interval, and 0.524 also lies within this interval. So these are good values. And of course 0 lies between negative 0.698 and 0.698, so we don't even need to check that one. So now that we've done that, we've found all of our inflection points within our interval. Now they just want them in ordered pairs, so we're just going to plug these back into the original function. So y of negative pi 6 equals 3 times minus pi 6 plus sine of 6 times minus pi 6. And then we'll solve for that. So the 6 and the 6 cancel. Sine of minus pi is 0, so that goes to 0. And 3 times negative pi 6 is negative pi halves, right? Because the 3 and the 6 cancel to it too. So our first ordered pair for an inflection point is that when x equals negative pi 6 and y equals negative pi halves, there's our first inflection point. Now we're going to solve for what happens when we plug 0 into our y function. And this is our original y function because we're curious about the original graph. So y of 0, let's just check it out up here. 3 times 0 is 0. Sine of 0 is 0. So we know that's also going to equal 0. So here's our second ordered pair, 0, 0. Now we're looking at pi 6. Now when we plug in pi 6 for y, we end up with 3 times pi 6 plus sine of 6 times pi 6. Well, the 6 and the 6 cancel. Sine of pi is 0, and 3 pi 6 is pi halves, a positive pi halves. And there we have our 3 ordered pairs. These are the inflection points. The inflection points within our function's domain. There are probably more inflection points off to infinity and negative infinity, but we're only curious between these 2 points. The real trick here is knowing how to write your arc functions as an infinite sequence of sorts. So this is part 1. I'll do a part 2 in a little bit here. I hope this helps. Have a nice day.